Good morning, calculus students. We're a little pressed for time, so I'm going to skip 3.1, but I do want to do a little preview of it because it kind of shows the big picture. There won't be any specific homework on 3.1, but I wanted you to see where we're going with this whole pre-calculus limit and calculus ideas. Here's the preview of calculus in the book. You can read it in more detail. But this limit process that we're going to talk about makes a connection between what we're going to do in pre-calculus, what we did last year, and what we did in review this year, to calculus. Some of the things we've done without calculus is just find values of a function by putting c into a function. We're going to see that sometimes the function right there is not defined, like the holes we talked about before. So we can figure out what the limit of f of x is as x approaches c. We've done a lot of slopes of lines in the past, all the way back in Algebra 1 by using the slope formula. Now we'll be able to come up with the slope of a curve, defined as the slope of the tangent line to the curve at a single point. And that's essentially the difference between average rate of change and instantaneous rate of change. For the average rate of change, you take 2 points and look at their distance and divide by time. The change in distance over the change in time. But here, it's the instantaneous rate of change right there at that point on the curve. We're not going to get into curvature of circles so much. Here we go. Area. We were very much limited to the formulas from geometry before. Now we can look at the area under any function. We'll do that in the second semester. Work is one of the applications of area. And these other things are more advanced topics. We might get to some volumes of rotation problems. Now, right after the limit chapter, in chapter 4, we're going to do the tangent line problem. And we've talked about this before, that it was fine when we were doing secant lines and you'd come up with the slope of a line between 2 points on a function. But now how do you get the slope at just that single point? And I'll do a much more detailed explanation of this later. This is just to give you a preview of why we're looking at the limit process. Because here's the formula for the slope of the secant line. And as delta x goes to 0, we start getting 0 over 0. But if you look at the process of what happens with all these successive secant lines, the limit, as they get closer and closer, will form our tangent line. And a similar thing happens when you look at area under a curve. Here's the area problem. We used to be limited to just geometrical areas, but now we can break up into an area under curve as smaller and smaller rectangles. That will get a better and better approximation. And here's another example of the limiting process. As we let this number go to infinity, the estimate will get better and better and better. We'll eventually get the area of the curve. Okay, so that's a little preview of where we're going with calculus and what we're going to take on this year. Back to the chapter. Finding limits graphically and numerically. We're going to do that. We're not going to focus so much on just the formal definition. In the interest of time, we're just going to focus right now on sort of the visual idea of the limit. Now, when we look at this problem, x cubed minus 1 over x minus 1, x can't equal 1 because you're dividing by 0. But when you simplify it out, you do get this curve that approximates it. So we can see what's happening as we get closer and closer and closer to 1, as we approach from the one from the left and one from the right. Here's the numeric analysis of it. And you can see, look, it looks like you're getting closer and closer and closer to 3. Now, how do you get 3 from this equation? Well, you'd have to factor it out. And that's one of the things we're going to practice in the second section, is how do we deal with a rational function like this and finding its limits. Right now, this is just sort of the visual approach. And so here's the idea of the limit. The limit as x approaches 1 of f of x equals 3. So the limit is referring to a y coordinate that we're getting closer and closer to as an x coordinate gets closer to something. Here's what we use for our definition for right now. An informal definition. F of x becomes arbitrarily close to a single number L as x approaches c from either side. And that's the limit of f of x as x approaches c. The limit as x approaches c of f of x equals L. As x gets closer and closer to c, f of x is getting closer and closer to L. Now, again, we look at a way of estimating a limit numerically. In the next section, 3.3, we'll look at how to do this algebraically. But for right now, you can rely on either a visual representation or your calculator to try some points. As they get closer and closer, as x gets closer and closer to 0, what's going on with f of x? If you just plug in, it doesn't do you much good because you get 0 divided by 0. But you can see clearly visually that this is getting closer and closer and closer to 2 in the numerical analysis as well. Now notice the fact that at 0 itself, function is undefined, doesn't have a bearing on the limit, because the limit is talking about the behaviors of the function as we get closer and closer to that point. Not what's going right at that point, but what does all the other points seem to be saying they should be getting closer and closer. Now, ways of finding a limit for it now are a numerical or graphical approach. The analytic approach is what we're going to look at in the next section. But see, in this case, we can look at the graph of f of x equals 1 when x isn't equal to 0 when x equals 2. So it's a piecewise definition. It's very strange. It's essentially a horizontal line for everywhere but 2. But then at 2, we put the point down here. Does this still pass the vertical line test? Well, yes, because the vertical line through x equals 2 will only hit 1 point because we put a hole in the horizontal line right here. So what will be the limit? Well, as we approach 2 from either direction, the graph clearly says, oh, we're getting closer and closer to 1. But then right at 2 itself, the function is equal to 1. So you have to deal with this disconnect. That here in this case, the limit as x approaches 2 of f of x equals 1. But f of 2 equals 0. When these two don't agree, it's called a discontinuity. That the function seems to be pointing the points in one direction, but the actual value at that point is down here. Now, let's look at some examples of behaviors that differ from left to right. Here goes, show that the limit as x approaches 0 of absolute value of x over x does not exist. We'll look at this visually. From the definition of absolute value of x equals x if x is greater than 0, greater than or equal to 0. It equals the opposite of x if x is less than 0. So it's a piecewise definition. We have to think of it in two parts. So our little function here, this f of x equal to the absolute value of x over x, will also split up into two parts. When x is greater than or equal to 0, we're just going to get absolute value of x equaling x. So the whole thing will just equal x over x or 1. But when x is less than 0, the absolute value of x will equal negative x. So we'll get negative x over x, so that's negative 1 when x is less than 0. So in terms of a picture then, when x is greater than 0, we're going to get 1. When x is less than 0, we're going to get negative 1. And so we get this picture of something that's very strange. To agree as we get closer and closer to 0, the limit as x approaches 0 from the right, that's what the little positive means, of absolute value of x over x is equal to 1. The limit as x approaches 0 from the left, the absolute value of x over x equals negative 1. So therefore, the limit as x approaches 0 of the absolute value of x over x does not exist. Does not exist. And so we're going to use a little abbreviation for that, DNE, because the function just doesn't agree with what should happen. It's not the fact that the function itself does not exist. We established that right away, because you can't divide by 0. It's also the limit of the function doesn't exist, because the direction limits don't agree. Now here's another case where the limit does not exist. The function has a vertical asymptote here at x equals 0. But also, we see that the limits don't exist because they're not getting closer and closer to a fixed number. So the limit as x approaches 0 of f(x) does not exist. Let's take a look at number 14 here. The limit as x approaches 2 of f of x, and f of x is defined in pieces as x squared plus 3 when x is not equal to 1, but 2 when x equals 1. So we've got a hole here, but the function is defined everywhere because they said at x equals 1, it should go to 2. So, but what's the limit? F of 1 equals 2, but the limit as x approaches 1 of f of x, we have to look at all the points that are around 1. What do they seem to be closer and closer to? Well, they seem to be working on this function. And we get 1 squared plus 3 and 4. Here's this hole at 1, 4. And all the other points of the function think that that hole should be filled with the point 1, 4. But the function itself is defined as 1. And it's defined as 2 at x equals 1. So we seem to have a disconnect here. The limit as x goes to 1 of f of x equals 4. But f of 1 is equal to 2. This makes f discontinuous at x equals 1. It's called a discontinuity, sort of a break in the function. A continuous function is something you can draw without lifting up your pen or pencil. But here we have to lift it up here and then put it back down here. And that discontinuity is there at x equals 1. Let's try one more. Okay, here in problem 41, we're trying to find both the limit as x approaches 4 of f of x of this function, and also what its domain is, and we're just going to look at it graphically first to see if we can answer those questions. Well, on the graph, on my first attempt at graphing this on GeoGebra, I get this thing that looks like just a flat line. That's because my scaling could probably use some adjusting. Also, you might want to change your window so that you actually see where the function starts, and it's over here. And that certainly seems to make sense because x plus 5, the thing underneath the square root, has to be greater than 0. So x plus 5 is greater than or equal to 0, so x is greater than negative 5. So that seems all just fine. But what's going on at 4, though? Let's try and take a closer look. I stretch out the graph this way. You might want to change your zoom to, only as high as like 0.4 or something like that. So you can start to get a sense of what's going on with the function, what's going on this way, too, as we stretch this axis over. As soon as you keep it getting smaller and smaller. But what is actually going on at 4 itself? Well, if we put a point on the function and start sliding it around, and let's put a little more accuracy on this so that our rounding is to 4 decimal places. There we go. And now, as we pull this and get closer and closer and closer to 4, as we approach 4 from the left, It looks like it's getting closer and closer to 0.1 something. Oh, I went past 4. So it looks like we'll have to come up with a numeric estimate for this. Maybe 0.16 we're up to. Right at 4, right at 4 itself. It's hard to get there exactly. But maybe we can have the calculator help you by looking at x equals 4. On your calculator, you can just type in 4 during the trace, and you'll see it's blank. If we do x equals 4 here, there's the vertical line, and now I want to look for the intersection of those two. Intersect those to come up with a point. And notice B, this point of intersection, is undefined. Because technically, when you put 4 here, you're dividing by 0. But it's one of those examples of a hole again, where if I put 4 on the top and the bottom, it makes 0 on top and 0 on the bottom. And that indeterminate form, so we're really going to study a lot in this chapter. So it looks like A was trying to get closer and closer and closer to this point. But right at 4, it's undefined. So we have to use a numerical analysis to say, well, on either side, it looks like a 0.17. That's where we could say that 1 decimal place, 2 decimal places, maybe 0.166, which is roughly. Okay. So getting back to our drawing board, we have a domain restriction here. X must be greater than or equal to negative 5. Of f of x. Just do it by direct substitution, but it looked like it was about. You can actually ask your calculator this a bit too. So get out your 89s and see what the TI-89 says. Okay, here's where I typed in my TI-89. I put in TI-89, a limit in the calc menu of the F3 calc menu of the home screen of y1 of x, x comma 4. So you have to tell it the function you're taking limit of, what the independent variable is, and what value x is approaching. And it does exactly what it's saying. That's consistent with our little results over here. Okay? Now, to do it this way, I had looked at the graph of y1 of x, so it was handier just to call up this. You could also just put in the whole limit again, all that stuff. All right, flange